In this example 6, we're going to demonstrate again the applications of the logarithmic function. Now, the important point here is that you have a function y defined to be a complicated functions of x squared plus 1 times x plus 3 to the power of 1/2 over x minus 1 for x defined to be larger than 1. So if you were to calculate the derivative of y with respect to x, it will be very complicated if you apply the quotient rule for derivative. So you have to calculate the derivative of this times this plus the derivative of this times this term, and then you also have to calculate the derivative of the term in the bottom, and you have to combine the denominator and the numerator in a very complicated manner. The easier way to perform this kind of derivative is to convert or to take the log of the y function. Now, before we take the log of, before we proceed on to calculate the derivative of y, let us try to look at the sort of like the structure of this function y. It is understood that the function y is made up of an division between an numerator and the denominator. When you take the log of y, what you effectively does is to convert the derivative into the form of an subtraction. So here, this equations is involving the operation of division between the numerator term and the denominator term. When you take the log, this equation is now converted into the form that involves the difference of two terms. Which one do you think is easier to calculate? The divisions of two terms or the difference of two terms? So the divisions of two terms is easier always. So here it demonstrates again the convenience of taking the log. You can effectively convert the operations of division into the operations of an subtraction. Then it is easier to calculate the derivative of the difference between two log terms. It is easier than to calculate the derivative of the divisions between two terms. So here, let us proceed with these calculations. You can further simplify the expression on the right-hand side of the term by using all the rules that we have learned. So this is just x squared plus 1 plus the log of x plus 3 raised to the power of half, and then you can further reduce these power terms into the product of the power of half with the log term. Right here you have log of an power term. Now here is the product of two terms. There's no more power terms after you have taken the log. Then you have this log of x minus 1. So you effectively have converted the expression of the function y into the additions of three log terms. Additions of three log terms is easier to deal with than the product or the divisions of three terms. So you can then easily take the derivative of the equations. So you take the derivative on the left-hand side, and what you get is that you're going to apply the chain rule to the left-hand side. Then you have dy dx, and then you have 1 over y. 1 over y comes from the fact that this is the derivative of the log of y with respect to y. Then the right hand side is just the derivative of the functions of x squared plus 1 in the log. Then this would give me ddx of ln x squared will give me 2x over x squared plus 1. So I write down this by referring to the fact that the derivative of an function u, so ddx of a function of u is just simply equals to 1 over u du dx. So using this very simple rule, then I can calculate the derivative of the log. Sorry, not this one. Yeah, here I'm using u as the log of x squared plus 1. So I call this u, which is equals to ln of x squared plus 1. Then I can easily calculate the derivative of the log to be just given by this expression using the derivative of the u. Then the other term would be the derivative of this, which is 1 over x plus 3. Then this last term would then be equals to 1 over x minus 1. So that allows me to calculate the dy dx times y is equals to the right hand side. After some small rearrangement, I can then express dy dx to be just dy multiplied with the sum of the three terms, which is 2x over x squared plus 1 plus 1 over 2 of x plus 3 minus 1 over x minus 1, where the y is just the expressions of this complicated expression. Okay, here this is a y, so I might just as well leave the expressions in terms of y instead of writing out the full expression of y. So that is how you can use the natural log to perform the derivative of a complicated algebraic function. So the point here is that you convert these equations into a form that involves the log. When you do that, you are actually making the product or the divisions into the sum in terms of the log, so that when you take the derivative, it's easier because you are taking the derivative of the sum of three terms. That is much easier than taking the derivative of the ratio of three terms. So one does not simply understand logarithm. So here logarithm is not simply an function to be memorized. It is the beginning of many important consequences. So to conclude this lecture, we have first defined what is the natural log, and we have discussed some of the important properties of the natural log. We also mentioned what is the derivative of the natural log of a general function of x, and also from here we derive a very important behaviors of the integrations involving 1 over u, and this will give us the antiderivative of 1 over u in terms of the natural log. Then we also show that the natural log has followed a set of very important rules, which is given in theorem 2. With these important properties, then you can simplify the expressions involving logarithm. Finally, we show that you can use the logarithm to simplify the differentiation of complicated functions, because when you take the log of a complicated function, you can break down the functions, like in this example, from a product of many terms into the sums of many terms, and that allows you to take the derivative in an easier manner.